Hey guys, Mr. Newman here. We're going to be learning about completing the square and vertex form of a parabola, and we're actually going to get into circles again. So, first of all, I wanted you guys to notice all these perfect square trinomials. Aren't they perfect? Aren't they square? Why in the world are they perfect and square? Well, it's because they are equal to a binomial squared. The first one is x plus 3 quantity squared. The next one is x plus 5, all of that squared, and the third one is x minus 6 squared. Now, a lot of people make mistakes here because they say, hey, what if I square x plus 3? Isn't that x squared plus 3 squared? And no. It is not. Let me show you why. Remember, when you square something, you have x plus 3 times x plus 3. That should be FOILed, or I prefer the Punnett, using the Punnett square. When you multiply this out, remember that you get those middle terms, 3x plus 3x. And those middle terms are saying, don't forget me, so make sure you don't forget them. When you add all that together, you get x squared plus 6x plus 9. Now, look at these perfect square trinomials, and I want you to notice something about them. Do you guys notice how that 9 is always the square root of the 3? The last term of the perfect square trinomial is, if you square root it, is always the last term of the binomial. And that makes sense because that last term is squared, is the only thing that doesn't have a variable on it. You should also notice, so yeah, square root of 9 equals 3. You should also notice that that middle term, 6x, if you take away the x and divide the coefficient by 2, you always get that second term in the binomial as well. 6 over 2 is 3. So for example, 10 over 2 is 5. What that means is that we can always get the last term and the middle term on the perfect square trinomial. Those should always be related, where you take the middle term, divide it by 2, and you should always get the last term when you square it, because 5 squared is 25. On this bottom one, you have negative 12. It still works even with a negative because a negative 6 squared becomes positive 36. That is always true. So what if we want to finish a perfect square trinomial? Let's say I only gave you the first two. Well, what you would do is you would divide that middle one, or what will become the middle one, the 8x, divide the coefficient, just the 8, divide it by 2. You get 4. When you square it, then you get the last term, 16. And if you don't believe me, write down x plus 4 squared and multiply that out. Now, I wanted you guys to factor it anyway. That is the factored form, x plus 4 squared. And if you multiply that out with with either foiling it or with a Punnett square, then you'll get x squared plus 8x plus 16. Let's try this next one. Check. What would you get if you had x squared plus 14x plus something and wanted that to be a perfect square trinomial? Well, half of 14 is 7. 7 squared is 49. So we'd get 49 being our last one. Try this last one here on your own. Also, that is the factor. Did you get that we got negative 1 squared? Negative 1 squared is positive 1, so you should have gotten positive 1 there. And the factored form is x minus 1, all of that squared. Cool. So now we get to a tricky skill called completing the square. We kind of were just completing the square, but we were just doing it by filling in the blank. Here we're actually going to do it in an equation, and that makes it a little bit trickier because we can't just pick whatever number we want and throw it in and add it in there. We have to make sure that we don't change the equation. Notice that this first one is not a perfect square. X squared plus 6x plus 3 is not a perfect square. What we do know, if we had x squared plus 6x plus something, we do know that that blank would be a 9. So notice what I did. I did not ignore the 3. The 3 is off to the right. And I added, half of 6 is 3, and 3 squared is 9, so I added the 9 there. But we cannot just add 9. We have to keep the entire equation the same. So instead of just adding 9, I'm going to add 9, and at the same time, I'm going to subtract 9. You might think, wait, this is counterproductive. Why don't we just combine them? Well, our goal here isn't to get this as simplified as possible. Our goal is actually to get this in a form called vertex form for the parabola. And I'll show you why we call it that in a moment. But for now, let's just complete the square and then go ahead and factor that. So I'm going to put parentheses around the first 9 and around that first part of the equation there. And I know that x squared plus 6x plus 9 is equal to x plus 3. So I'm going to rewrite it like that. X plus 3, all of that squared. Negative 9 plus 3 is negative 6, so I'm going to just put minus 6. That right there is called completing the square because I completed the square and I kept the equation, the overall equation, the same. Now, if you plug in any number into that equation, any input for x, you'll get the same output for y that you would have before. So I'm going to box that right there. Go ahead and try this one on the right here. Try completing the square just as I did, and I'll show you in a moment how to do it. All right, did you get it? Let's find out. I drew a big blank here. I'm going to do half of negative 8 is negative 4. Negative 4 squared is 16. But I'm also going to subtract 16 so that I technically add nothing to the equation. And we put that in parentheses, so we get y equals x minus 4 squared minus 11. That is completing the square. That is called vertex form. So why are we doing this? Well, it's because it's called vertex form. And let's look at this last one here. Vertex form looks similar to our original function. So what's the original function here? The parent function, the original function, is y equals x squared. You guys know from function transformations that minus 4 is going to make or transform the entire parabola 4 units to the right because it's an input and it does the opposite of what you expect. The 11 translates that parabola down 11 because it's on the output, on the outside of the function. So we know that the new vertex, which was, the vertex was at 0, 0 for this parabola. The new vertex is at 4, 11. And you can see that in the parabola because it's in vertex form, 4, negative 11. That is one of the reasons that we complete the square in order to put things in vertex form. So go ahead and try to change this next one, change it to vertex form, and then give the vertex. And what I mean by change it to vertex form, in other words, I mean complete the square. Okay, go ahead and try. All right, did you get it? Let's find out. So, plus blank. I added 4 because negative 4, half of that is negative 2, and negative 2 squared is positive 4. That right there is the same as x minus 2 squared, and then minus 3 on the outside. So what is the vertex? The vertex is positive 2, negative 3. Notice the x value is always the opposite of what's inside the parentheses. So let's bring this full circle, back to working with circles. We have standard form of a circle is this right here. And we like this because it is easy to see the center. It's also easy to determine the radius. You guys know that the center is 2, negative 3, and the radius is 5 because that's the square root of 25. Let's go ahead and multiply that out and square those. So I'm going to square each of the things in parentheses and get rid of the parentheses. So x squared minus 4x plus 4, then plus y squared minus 6y plus 9, all of that equals 25. I'm going to rearrange it a little bit. Let's put the squares first in the equation. So x squared plus y squared, then the variables with a single power, negative 4x minus 6y, and lastly, I'm going to move the 25 over to the left, and we're going to have all of the constants together. We can combine all those constants, 4 plus 9 minus 25, and when you do that, you get the equation of a circle in expanded form. Notice how the squares come first, x then y, x squared then y squared, then come just the variables themselves, x and then y, and then lastly, the constant, and it all equals 0. This is standard form. And you can get that by multiplying out the equation, this is expanded form. You can get that by multiplying out the standard form equation and shifting around the variables. So what if we were given an equation in expanded form, knew it was a circle, and wanted to find the center and radius? Well, we'd have to convert it back to standard form. So let's try that. Here, we do that by completing the square. So I'm going to rearrange the x's, put them next to each other, and put a blank after the x's. I'm going to rearrange the y's and put a blank after the y's, and then the last constant, he'll be by himself, but not for long because we're going to complete the square. I know I need to add 9 and then subtract 9 because that completes the square for the x's. I also know I need to add 9 and subtract 9 because negative 6 divided by 2 is 3, negative 3, and that squared is positive 9. I complete the squares, so I can put these in parentheses, and I get x plus 3, all of that squared, plus y minus 3, all of that squared. And if I combine all the constants and move it to the other side, you find out you get 16. So the center is negative 3, comma, positive 3, because remember, the center of circles acts like the inputs. It's the opposite of what you expect, or the opposite of what you see. And then the radius is going to be 4, because the square root of 16 is 4. So notice how I completed the square twice, once for the x's and once for the y's, and I could change expanded form into standard form. Go ahead and try that on this last one and write down the center and the radius. And I'll show you how to do it in a moment. All right, did you get it? Here's the work. We're going to add 16 and subtract 16 and add 1 and subtract 1. There we are, factored out. So we know that the center is negative 4, comma 1, and the radius is 5. Thank you very much for watching.